So this is not a terribly polished talk. In January, I was asked would I like to speak at this meeting on experimental design and inverse modeling. And I thought, well, I'm at the Isaac Newton Institute. I've got nothing else to do. I can actually come up with something. And I've come up with some ideas, but it's not terribly polished. And I suspect you can come up with better ideas when I go through what I'm going to do. But the idea is, building on the sort of stuff that Angela was talking about, we have observations in the physical world, and we have computer experiments. And how do you balance your budget between spending on real-world observations and spending on computer experiments to do that inverse problem? And oops, I should thank some people who the example I'm going to show uses a HARP model from Steve Niederer and Sander Land at King's College, and the work on the example was done by a student at Exeter, Lorik Ferra. Okay. So, inverse methods combine numerical models and real-world observations, and I've sort of said this before, and we carefully design where we run our models, but we often don't carefully design where we do our physical experiments. We take physical data often off the shelf, or it's just given to us by our collaborators. And I'm going to look at sequentially doing both. So we're going to sequentially do the computer experiments. We've talked a lot about sequential design for computer experiments during this program, but I'm also going to sequentially do some design in the real world. And we're going to look at the cost of doing that. So there's a trade-off between the cost of running the computer model and the cost of collecting new observations. And I'm going to do it in the context of history matching. And Michael talked about history matching yesterday. But I'm going to go through it again because I know Danny's going to talk about history matching, and I think Jeremy's going to talk about history matching as well. So I'll try and explain history matching, and then you'll have the context for what I'm talking about. So it's a form of inverse modeling, but instead of trying to find the best value of the model inputs, we rule out those parts of input space that give implausible models so far from the data that you don't want to consider them anymore. Okay? And we do this by running our computer model, comparing it with the data, and ruling out space, and then within the region that we haven't ruled out, which is often called NROI space, not ruled out yet, we do some more runs and we shrink down the space until we get a very small space, which might actually be 0. We might rule out all space, or we get a space that doesn't shrink anymore and we say, well, we've finished. And in practice, what we do is based on this idea of implausibility. And that's the scale distance between the data and an emulator of the model, because we want to produce this everywhere. So this is a function of the inputs, and my inputs here I've written, I always do that, I've written as x. So we have the observation, and then we have the expected value of the emulator. Sorry, I missed the expectation there. We have the expected value of the emulator at some value x, and then we scale and we square that, and then we scale that by a series of variances. So we have the variance of the emulator, which we know that comes out of the emulator process. We have the variance of the observations, which we probably know because the person we're working with who took the observations told us that. And there's a discrepancy variance that models that bias term that Angela was talking about. The fact that our model isn't correct. Our models are never correct. And we history match in waves. We run the model to some space-filling design, build an emulator, rule out the regions of input space where that implausibility is large. Normally we use 3. It's a slightly arbitrary number, but it seems to work. It's quite conservative. And we just keep doing that until we get to some stopping rule. Now, the first step in each wave, if we go through this procedure again, is a design step. So we design a set of model runs to sit inside our current NROI space. And there are a number of proposals for doing that. I'm not going to go into the detail how you might do that. But we're going to say that we have a design that sits inside, or a set of candidate designs that sit inside our current NROI space, and that consists of n runs. And I'm going to put that as fixed. We run n runs at a time. This might be because we run n runs in parallel on our computer. And each one of those is going to cost c. So each wave costs us nc units, or whatever cost is, pounds, or whatever. Now, the results of each wave reduce the size of NROI space. That's the whole point. We're reducing the size of NROI space down. If we stop reducing it, then we stop doing history matching. We say we finished. But if you think of the formula, if I go back to the implausibility formula, we can reduce the size of NROI space by reducing this, or by reducing these. This one is pretty fixed. We're not going to remove the discrepancy. Our model's not going to get better as we go through the history matching process. So I could also reduce space by changing the observations, as well as by changing the emulator. And that's what I want to investigate a bit. So let's assume that a real-world observation costs Q pounds. So I've got to balance the cost of NC pounds of running another wave against the cost of Q pounds of collecting a new observation, but I also need to know how much benefit I'm going to get in reducing the size of NROI space by spending those, oops, I keep doing that, NC or Q. Now let's think about this in terms of example. The example that got me thinking about this problem, which is some work I've been doing on diastolic heart disease. So diastolic heart failure is an untreatable cardiac condition. It affects about 450,000 people in the UK. The heart becomes stiff and therefore doesn't beat properly. There have been 9 drug trials to try and produce drugs that would treat diastolic heart failure, and all of them didn't produce a successful medication. Now, the people I've been working with claim that the reason for this is that diastolic heart failure is not a single condition, it's lots of conditions, but we call them all diastolic heart failure. So when they do the drug trial, they try it on everybody, and it might be that some of those conditions within there they could treat with the drugs, but they fail the trial because the trial's across everybody. So their hypothesis is that diastolic heart disease is several different diseases, and they wanted to use the modeling, or they want to use the modeling of the heart to try and differentiate between these different diseases. Now, I'm going to report on a case study we did, and we're not going to do anything as ambitious as that. We're going to take one healthy patient and one unhealthy patient and see if we can use the data and the model to separate those two out. Okay, so that's step 1. come on. Yeah, okay. So this is the model. So it models the geometry of the heart, and that's a single beat. And we have data, and if I can get this to work, this is an MRI scan, and they take the MRI scan and they segment it and put it on the same grid as the model. And we can compare the two. So first we have to build an emulator of that cardiac model. It's very high dimensional output, so we have to reduce the output. The model itself takes 6 hours to produce one run, which is one beat of the heart. It's a lot slower than you are. So it's a relatively expensive model. We build a Gaussian process emulator, and I'm going to just give the results for the first principal component, but I've put principal component in quotes because it's not actually the principal component. It's the modified version from this paper here by one of Danny's students. And if you want to know about the modification to the principal components of the output, ask Danny afterwards, and he will explain it to you. It just makes the model principal component closer to the data. And we project the data into that space, so we have a comparison between the data and the first principal component. So now I'm going to do NROI for my first patient, and I'm only going to show the results for the first patient, but we actually want to do NROI for the patients with the condition and without the condition, and hopefully when we do lots of patients, these will cluster into different clusters, and we can go and help doctors do that. But even if we can just separate out healthy patients and unhealthy patients, this would be a useful diagnostic tool. Particularly because the cluster, you could just cluster the MRI scans, but clustering the model inputs gives you some biological reason for the clustering, and that helps with trying to work out exactly what's going on in the condition. So we history matched I'm only going to show the healthy patient. So this is the result of wave 1 of history matching, and you get, well, we produce these really horrible plots which shows the effect of the history matching. So let's have a look at what this means. So we do this history matching, and we remove 75% of parameter space in the first run. And if you look down the leading diagonal on this plot, that's the marginal of that parameter after that wave. So there's wave 1, and this parameter has changed a lot in the margin, and this parameter has changed very little in the margin. But these plots show the probability of finding a point that's in, as you look through, the proportion of space as you look into, what is it, 20-dimensional space through this 2-dimensional window. And down here is the maximum of that implausibility. It's an attempt to look into this 20-dimensional space. We discovered one thing, that these two parameters actually, the inputs do exactly the same thing, so this is always a straight line. The modelers did actually know this, but why they had two parameters did exactly the same thing, I don't know. In a sense, it gives a nice check that our emulator is working, the fact we do get a straight line. So that's the first wave. 25% of space remains. Second wave, we're down to 6%, and we can see that this parameter is the one that's doing all the, well, doing most of the work, along with this one in the margin, but we're also getting these sort of twisty structures inside the 20-dimensional space. That got us down to 6%. Wave 3 got us down to 5%, and we stopped because we weren't getting any real improvement. If we didn't have a discrepancy in this history match, this goes to 0 at wave 3. So initially they said it's a good model, so we ignored the discrepancy term. I have to say most people ignored the discrepancy term to start with, and they put it in afterwards when they need it. And wave 3 went to 0 space, and that's saying there is no way this model fits the data. And then we went back to them and they said, yeah, well, the model does it as a fixed top and bottom to the heart. The real heart moves up and down, so we don't have that in there. So we came up with a good value for what that error might be. And if you put that the discrepancy term in, we get this result, and we get 5% of the space still left. So we've got a fairly small, 5% of 20-dimensional space is still quite big, but we have a fairly small region of possible model hearts that fit, but are not inconsistent with the data. And we did the same thing for the unhealthy patient, but I'm not going to show you that result, but they are separate. We can separate the two out. That's basically what I just said. Now, if we go back to the design problem, what I want to know is if I do another set of runs, another wave, which is what I've done in this case study, that will reduce NRI space, but I could go and get another MRI scan, and that would also reduce NRI space because it would reduce the observational error. And how do I balance those two? And how do I balance that two without actually spending any money? I don't want to do any runs, I don't want to get any MRI scans, because both of those are expensive things to do. So if we go back to the implausibility formula, this top bit, the numerator here, the y observations is sort of the expected value of the observation. So I don't expect that to change. It will change when I collect the observation, but I can't predict how it's going to change. And similarly, this is the expected value of the emulator. And okay, I'm going to run the emulator at new places, but I'm just going to get the expected value. That's not going to change either. So the numerator is a bit of a dead loss of predicting how I'm going to shrink my NRI space. Now, actually, most of the action is going to occur here because I'm going to get a much better emulator, but I can't predict how much better that emulator is going to be given the information I have. What I can predict are these variances. So we can't do better than the emulator we've got without doing some more model runs. So we can calculate the variance at every new proposed design point. And those are going to be inside our NRI space, so they're probably going to be smaller than the variances for the points outside the NRI space. There's no reason to believe that I have any data, any current runs inside that NRI space. There's no reason to assume that. So we can calculate the variance at each proposed design point, and that's a measure of how well that emulator is doing. And small variances would reduce the NRI space, so I'm going to take that variance as a proxy for how well the emulator is going to reduce the NRI space. I say most of the action actually happens at the top, but I can't predict that, so this is a bad proxy, but it's the only thing I've got. Now, think about the observational error, and again, not much I can do about the numerator. It's the expected value. That's what I'm going to expect. But I can look again at that variance. And if you think that the observation is a mean of a set of numbers, then I can look at, if I collect another observation, that mean the variance will fall according to the standard formulae we all know. And we can calculate, if I add an extra point, how much that variance is going to decrease. And there's a diminishing return as you collect more points. The effect on the variance is smaller and smaller. So that implies as I go through the waves, an extra data point isn't going to be that much use. But we saw from the example that some more model runs isn't that much use in reducing the space. The spectacular stuff happens at the beginning. So that's not necessarily a big problem. So we can just balance these two. We can predict the reduction in those variances and use those as a proxy for reduction in NRI. But actually, the observation variance can get a lot more complicated than that. If we go back to our healthcare example, we can split that observation variance, which there's a multitude of sins packed into that multitude observation variance. There's the subject variance, the variance in the individual. If you take an MRI scan on my heart and then you take an MRI scan tomorrow, you're not going to get exactly the same data. There's variance there. But there's also the population variance. We're not really interested in particular individuals. We're interested in populations of people who are healthy or have the condition. So there's the variability across the population, and that gives us this point. Do I call in that individual for another MRI scan, or do I go and find another patient and take an MRI scan? And whichever is predicted to reduce that variance the most is what I would do. But then once you get into the world of real-world experimental design, we might be balancing for age or blocking for gender or other covariates. So it gets a bit complicated, or could get a bit complicated. But the idea I'm proposing is actually very simple. So we can calculate we know the cost of a new observation or a new set of model runs, and we can calculate this benefit, the variance reduction, and the average variance reduction for the computer experiment and the real variance reduction on the observation, and that gives us a measure of how much NROI might be reduced. These are ideas I've been thinking over the last few weeks, so I haven't got any calculations to show you how it might work, but I think it's simple enough that everyone can probably work out how you might calculate these things. It would be interesting how it works in practice. Certainly in terms of the healthcare example I showed, I suspect MRI scans are so expensive compared to computer time that we wouldn't really call in a new observation until NROI had stopped, basically, until we couldn't do any better with a computer, obviously in which case a new observation might enable you to reduce that space a bit further. Okay, thank you very much.
So I'm going to be provocative.
Oh, please do, Henry.
You've been hearing about history matching. Shouldn't the job of the physical experiment be to bias correct the computer experiment If you keep removing bits where the computer experiment does badly, you're sweeping the bias under the carpet. Shouldn't you just, you know, which is what Angela did. She used the physics experiment to correct the computer experiment, not to throw away bits where it did badly.
The bias correction is sort of done in that discrepancy term. So that discrepancy term says if the model can't get better than that discrepancy term, it can't get better than that bias, which we cast as a variance rather than a bias. So that sort of guards against throwing out stuff that might be useful. But the model can produce, the model inputs across the full set of parameters we can produce. So if I go back here, if I go to one of these horrible plots. So we start off with our space filling design where this marginal would be uniform. But we've thrown out stuff here, but that stuff is hearts that are completely not like human hearts at all. I didn't mention there's another facet to this experiment in that we did have a lot of problems of the model not running to completion. And that's not because the model was crashing because of some numerical problem. We just made the hearts so stiff they couldn't beat. So to run the model for a full beat, they just couldn't do it. So those models should be excluded from any experiment we're doing. So we're only cutting out things that are so far away that they couldn't be near the data. Now, once we've got down to this small space where we now believe the model that true optimal set of points live, the inputs live, then we can do a proper calibration inverse model living in that space that's now lost all the really crazy models that are nothing like the data. So we're not chopping out stuff that might be useful. We're trying to chop out the stuff that cannot be useful. Okay. That's why that 3, which is 3 standard deviations, is actually a long way.
Yeah, this might be a naive question, but I'm new to this. So how should I read this? This number 5% tells me that there's only 5% of the parameter space, but then I'm looking at the marginals, and they seem to have full support unless you're truncating somehow.
Yeah, because if you've got if I reduce it to that, the marginals have full support. So I've got a bent manifold wending its way through 20-dimensional space, and some of these parameters, the margin doesn't change, but it doesn't mean that somewhere in that space there's this bent thing. So just knowing this parameter on its own doesn't really help you do anything. This parameter, on the other hand, is very predictive on its own. That wasn't a surprise to them. Some of the others were.
And regarding the ratio of the implausibility, you
Yeah.
said you're disregarding the effect of the numerator. I understand that you cannot predict that.
I can't predict it, so
But
I can't use that in my prediction of how the NRI is going to shrink. When I do the experiment, I'll get the observations. That is going to make it shrink much further than those variance terms on the bottom.
so it is, even though, I mean, it's unpredictable, it is the major contribution to the...
Yes, it's just not predictable given the data we have. When I get new data, that's going to change.
Do one.
So I was gonna- So obviously, all sorts of scenarios where it's important to account for the discrepancy. But I just wonder from the application you described here, where you're trying to classify patients into different groups, you could ask the question, what's the best fitting model parameter for healthy patients and for unhealthy patients? and ignore discrepancy and just see what the best fits are. They might not be very good, but they still might be different. And whether, in this case, introducing discrepancy might just be blurring that diagnostic information.
Okay, so the way history matching works, if you don't have discrepancy and the model doesn't fit, if it doesn't get within those 3 standard deviations, your n-rise base goes to 0. You don't, it's not like standard inverse modeling where you always get an answer even if the model's really bad. I quite like this, the fact that if the model's really bad, it says this model's no good. On the terms you've told me, this model is not acceptable. And I think that's a really nice thing to go back to the modeler and tell them, because it shocks them a little bit that their model is so far from the data that it's not useful on the terms they've given. And that discrepancy term says how much error are they prepared to accept between the model and the data. Sometimes we call it tolerance to error. And I think that's a good term, because that's what we did here. We went back and said, how far could you be from the data? And they came up with some numbers. We didn't push them. They came up with the numbers that brought it in so that the model was now within a distance. But it's a distance now we know that we had to add that extra term. So it doesn't always, if I didn't have a discrepancy term, this would just go to 0. It's not like a standard calibration where you always get a number which is the closest you can get, even if that is very, very far away.
So, the big problem you talked about, the one heterogeneous situation where the drug works on some people and not on others.
Yeah.
So you could take this further, and then you're now beginning to think about discrepancies in one group and discrepancies in others. And so you're doing also a sort of population separation. So that would be very cool.
Yes, that's where we're heading. I'm not sure exactly how to get there, but yes, it opens up lots of interesting questions we don't normally get. You know, if you do climate, there's only one climate, and you just fit to the climate. If you're doing health, there's loads of people and they sit in populations and they have different groupings and such like, and exploiting that is going to be quite challenging but very interesting.
Okay, so thank you very much once again.